ferromagnet spin-triplet superconductor heterostructure. That's what.
Okay. Yeah, so before really going into my talk,
If you want to use.
no, I just need the pointer.
Pointer, this one.
Oh, okay. Thank you. Yeah, before really going on to talk, maybe I should really start with sharing some photos. So, yeah, I was postdoc with Shoucheng for 4 years, and it was very typical. Shoucheng always showed tremendous energy, and we worked on various different topics, mainly concentrating on the Majorana fermions in helium chiral topological superconductor and all. And yeah, the last time I met Shoucheng was last year, just before the March meeting, and it was very typical. I mean, he picked out how the Majorana braiding matrix and this scattering matrix of this quantum anomalous hole chiral topological superconductor I wrote down was actually identical, which to him was the clear sign that you can actually do topological quantum computation with chiral Majorana fermion. Well, he was teaching me about the papers I wrote, but anyway, that was very typical, and he was also complaining very loudly how D.A. Ivanov, who really started this field, is actually out of physics community altogether. That was all very typical, and you know, after this discussion in that fall, he invited me over to Shanghai for this workshop. In fact, this is the very workshop that Yulin was talking about yesterday dinner. But to me, there was another development. I mean, this became the first time I ever turned down Shoucheng. Well, so this is, but overall, I mean, this may be a new development for me, but overall, this is a typical case, like, you know. Yeah, well, he was quite unaware of this, and I guess, well, I must say the last time I met Shoucheng, I wasn't predicting this at all. But anyway, you know, this is another typical case, you know, like big boss stopped by ultimate boss, you know, that kind of thing. But I have to say that, yeah, I have to wonder, you know, the ultimate boss is maybe too overly lenient, because, I mean, just less than a fortnight after we returned from honeymoon, she somehow thought that it was okay to actually give me permission to go off to this workshop in India. Well, I think she really got fooled by this photo I showed her. This was my father taking me to Ajanta caves, I believe, 30 years ago. So I lived with my father in India for 3 years back in the 80s. So this was my first return to India in all those years. So I was really ecstatic to be back in India. Well, this is part of India I have never been to, but anyway, I was extremely happy, and I was about to give my talk, but I did something I should never do before beginning a talk, which is going to, you know, looking into my email, and maybe because it was from Xiaoliang, but so, I mean, all I can say about the talk is that, you know, I mean, I remember nothing about this talk. It may have been excruciating, it may have been just hypnotic, it may even have been borderline okay, but really, I don't know what happened between reading this email and actually coming back to my apartment in Korea a day after. And I guess certain things are completely, you know, certain things cannot be really scared in your life. I mean, I was just beginning my marriage and beginning my new life. And, you know, Shoucheng, of all things, I can say that he was the most alive human being I have ever known while he was walking among us. But, and really, this is the exact same slide I had when he invited me over to his 50th birthday, and really, I mean, showing this again in this kind of this circumstance is really, I'm still trying to, I am really at loss. This is not what anyone would have thought. But still, I want to really talk, I mean, along with physics, about how, what kind of viewpoint Shoucheng really taught me. And I thought that maybe it's better to actually talk about a project which never involved Shoucheng at any stage. You see, our chair Una was involved in what was kind of like the motivating project we had in the past, and this is work I worked on with my friends in UCLA. In fact, the last time I saw Shoucheng, I was on my way there to finalize the main work I'm going to discuss. So in this workshop, I mean, a big issue that was raised was that, how are you going to transport electrons without generating heat? Because if you are going to if you want to excite your system first, that means that you're increasing entropy, and hence you're going to generate heat. And this is one of the reasons why if you try to have spin current, they're actually suppressed after traveling some distance. They're going to be exponentially suppressed. And big focus during this workshop was, thinking about a single particle transport, which was really going just through the ground state, and hence involves no heat dissipation. And that would be some scenario involving Berry phase. But then there's another transport through the ground state, which should happen in superfluid transport. And when it comes to spin transport, certainly single electron spin current has been more discussed. And there's a very neat analog of this, showing how this soccer kick really, the soccer ball really bends because Roberto Carlos really put spin on it. But then the interesting thing was that, actually people back in early mid-'80s, people actually have seen spin current carried not by single electron, but actually by a Cooper pair of helium-3 atoms. And in this case, what they have seen is that this was arising from the order superfluid order parameter, and it was really transport through bulk. And really, this somehow should involve Cooper pairs that's different from the most conventional picture, where you have actually pairing of opposite spin, and hence, really Cooper pairing practically raises off the spin. So we actually need to go back to the this pairing gap order parameter to really see what's going on. So obviously, we are not in the spin singlet case, so we want to project out spin singlet part and just think about the spin triplet part to see how spin current can arise in this kind of spin triplet pairing. And the usual approach is that, once you project out spin singlet part, since there are this is 2x2 matrix when you're pairing up spin half electrons, what you would be left over, you would actually have some kind of like a 3-component vector that's left over. And they would be actually real up to, if you're not having a spin polarized condensate, they would be actually real up to overall phase factor. And the point about this real vector is that you can actually, the spin operator, the way it commutes with the spin operator, basically it's like this, the rotation of this d vector would be generated by the spin operator. So in this is not, d vector is not equivalent to spin, yet its rotation is generated by the spin operator. So in this sense, this D vector is actually has, in this commutation sense, completely identical to the Nell vector in antiferromagnet. So actually, in recent years, actually my collaborators have worked on how the spiraling of the Nell vector actually can generate spin current in antiferromagnetic insulator. So there's actually a very close analog between spin-triplet superconductor and this antiferromagnetic insulator. But you see, the interesting thing is you can get intuitive sense of how this kind of spin current or how this spin current arises much easier actually with the spin-triplet superconductor. And that would be easiest to see if we for the case when we confine our D vector to on an XY plane, say on a plane, say XY plane. Because in this case, the direction of the D vector within the plane is simply none other than the relative phase between spin up pairs and spin down pairs. So what this means is that any gradient in the direction of this D vector would be completely really, what that would actually give you is the counterflow between spin up pairs and spin down pairs. This is actually like the textbook definition for spin current, except that in this case, the spin current is carried by Cooper pairs. And certainly this can be generalized to general cases. So there is a very elegant formalism for spin current in this kind of spin-triplet superconductor just from looking at this order parameter. You know, and Shoucheng was kind of person who would ask, you know, so what's the consequence there? Can you make this really happen in physical system? And actually, before becoming his postdoc, this was the project with Una, which actually, where the spin current was actually very, very important component. So we first had to decide on what kind of physical system we would work on. And actually, at that time, the candidate seemed very obvious because, there was strong interest in strontium ruthenate 214 as the candidate material for spin-triplet superconductivity, because the night shift experiment at that time really suggested that somehow you didn't see any spin susceptibility change at Tc. So this was taken to mean that you have essentially equal spin pairing in the direction of the Zeeman field. And the point about the spin-triplet superconductor is that once you have equal spin pairing, one thing you can easily say is that you can think about a new topological defect. Instead of just having winding of 2 pi phase winding of the overall phase, in which case you would have circulation just of the charge current. The situation you can have for the spin-triplet superconductor is that you can have vorticity in only one of the components, say just the spin-up component. In that case, what happens is that around this kind of half quantum vortex, you would see circulation not just of the charge current, but also of the spin current as well. In fact, spin current is like the essential component to make this half quantum vortex work. Although, to be honest with you, even I was really motivated more by this possibility of having single Majorana zero mode there rather than the spin current. But then the problem I was really working out with Hendrik and Una, Hendrik, who is colleague of Karsten in Aachen, who is here, and Una, was that, this is very interesting, but is there any way you can stabilize it? And the stabilization really actually turned out to really involve spin current here, because whereas the charge current has Meissner screening, the spin current doesn't have any kind of screening. So if you try to have it in bulk, actually you are going to run into this kind of log divergence. And the only way you can work around that is to really try to nucleate one in the mesoscopic size sample, where you can actually certainly suppress both the screening effect and the log divergence. So this is what's kind of like gave the motivation actually for this half quantum fluxoid experiment at Illinois, because once you look at the magnetization curve for this fluxoid entry, you'd see this kind of double sawtooth pattern. So, it was very nice to actually have a chance to work talk and work with experimentalists, but I mean, even if we completely accept this spin current explanation for this half quantum fluxoid in this experiment, it actually leaves one question completely unanswered, which is the issue of like, is there any way we can have Cooper pair spin current in the bulk? I mean, this is just metascopic size sample, so can we really have something going on in the bulk? Yeah, so this was surely the question Shoucheng have asked if I really had time to get into detail of this project. But actually many years elapsed really without coming back to this question. But after going back to Korea, there was actually new interesting development going on. Actually, I feel a little bit guilty about the whole process because the material that gave an opening was something that was actually studied in Stanford as well, this strontium luthenate 113. This is a ferromagnetic metal, but it really has very similar structure to strontium luthenate 214. Hence, you can actually have a it's actually compatible. It's highly compatible when you want to make a heterostructure between 214 and 113. You can get a reasonably clean interface between 113 and 214. And the recent experiment back in Korea was that they have seen a very long-range proximity effect, a superconducting proximity effect into 113. So the easiest explanation here is that 214 has induced spin polarized Cooper pairs in 113 ferromagnet. And actually the inverse of this is that it must be, what this implies is that actually you should be able to inject spin polarized Cooper pairs from 113 into 214. In other words, what this means is that when you think about the Andreev reflection that happens at the 113-214 interface, the Andreev conductance there should have spin polarization. The Andreev conductance for majority spin should be different from Andreev conductance for minority spin. And hence, that's kind of another way of saying that how you can inject spin polarized supercurrent from 113 into 214. And once you inject in this kind of spin polarized Cooper pairs into 214, I mean, just from the Hamiltonian, the only conclusion you can possibly get is that you are having complete conservation of the spin current. So it's like saying that certainly you are going to have something that's infinitely better than having spin current exponentially suppressed into when you go into exponential suppression of the spin current. However, it should be, this is a solid state system, so we are not going to have any kind of SC spin conservation at all. So we need to consider what's like the maximal breaking of the, we have this spin-triplet superconductor which breaks spin rotational symmetry. So what's like the maximal spin non-conservation you can have? And the answer is that the maximum you can have is to have this set of finite lifetime for the condensate spin polarization. So, but even when we put this in, this does not result in any kind of exponential decay of the spin current with the distance. Rather, it just means much weaker inverse distance decay of the spin current at the most. So the result we get is that depending on whether we have spin alignment, magnetization alignment between source and drain or anti-alignment, the difference in the current for those two cases at the most really decays with the distance between the two leads. And so this is a phenomenon, this is all due to the spin current carried by Cooper pairs, which means that this kind of, the magnitude of this kind of magnetoresistance would be really proportional to the condensate fraction. So this would really have onset only at Tc. And this is also a bosonic picture. I'm not talking about any kind of quasi-particles here. And the convenience thing about this kind of bosonic picture is that you can actually also account for the collective dynamics of the D vector as well with this picture. So here you can actually have another nice toy model to really show the points here. And basic point is that since we are breaking spin rotational symmetry in spin triplet superconductor, we should also have spin collective modes in spin triplet superconductor. And they can be really thought of as being completely equivalent to pendulum. The pendulum angle would be just like the relative phase between spin up pairs and spin down pairs. So basically, what we can do here is that if we apply AC voltage between the two leads, what you can basically have is that we can have one of the spin component oscillate, but that's kind of like only spin up component oscillate. But that's pretty much you cannot do that without inciting, oscillation of the relative phase between spin up component and spin down component. And as a consequence, what you should be able to observe in this kind of observe with this kind of AC voltage bias is this kind of resonance effect. And the resonance will be different depending on whether you have magnetization alignment or anti-alignment. And again, there's a very convenient toy model picture. Like one of them you can consider to be like equivalent to closed pipe. The other you can view as an analog to open pipe. And so there's an experimental effort underway using strontium luthenate, but I also want to point out that there has been lots of different spin triplet superconductor candidate that's been floating around, especially with all the interest aroused by twisted bilayer graphene superconductivity. The real, I think, issue is more than anything to do with spin triplet superconductor candidate is whether we can find any compatible material, ferromagnetic metal, to inject the spin polarized Cooper pairs. And in the remaining time, I'll just mention briefly about what's the kind of like the limit, what's the robustness of this superfluid spin transport in this kind of system. Like how much spin current can you jam into a spin triplet superconductor? So this actually brings back something I have learned here actually from Mac Beasley, but the fact is that if you try to have too much spin current, what would happen is that you have just too much twisting of the phase, or superconducting phase, and at some point, rather than having full Cooper pairing, you would like to have some phase flip to relieve reduce this kind of phase twisting. And the worst phase twisting that superconductivity can endure would be if you have 2 pi phase winding just over the healing length of the order parameter, then more than that, the superconductivity will just collapse. But here the situation is complicated because we don't just have the overall phase to worry about. We also have the spin phase as well. That is to say, in addition to this kind of conventional vortex and also half quantum vortices, we also have to worry about the D vector meron. And the point is that, and you might ask, why do we need to worry about all of these? And that's because we are thinking about jamming in spin polarized current, which is to say we have both charge current and the spin current here. And we know that there's an energy change due to phase slip in the charge sector. The spin sector also must have this same type of energy change due to the Josephson voltage of the phase slip. So if you have spin polarized current, that will also induce, that will also create merons as well as the vortices. And in the simplest case where you have 100% spin polarization, what happens is that you have same phase gradient for the overall phase and the spin phase. But in the case where, say, the maron is much bigger than the vortices, which is to say the spin healing length is, d vector healing length is much longer than the overall phase healing length, what would happen is that you would come up against the spin critical current before you ever approach the charge critical current. So that means that the relative phase between spin up and down will be totally disordered, but you still would have the overall phase ordered. So this would be like the steady state analog of charge 4e superconductivity in that sense. Well, charge 4e must be nice. I mean, didn't Benner have his chariot dragged by 4 horses? And actually, there's a very nice picture to look at what's going on, because in this kind of regime, you would have diffusive spin transport. And when you combine that with this finite lifetime for spin imbalance, what you actually end up having is that the spin current, when you try to keep on injecting in more spin polarized current, the spin current actually gets, the spin relaxation kind of like makes spin current completely go away after some length scale, whereas but the same process actually leads to formation of charge 4e quartet, which carries the charge current completely unimpeded. So this is conclusion for my talk, and thank you very much for your attention.
Sorry for a naive question, but does charge 4e superconductor means there's a 1/4 strength vortex?
Oh yes, then the signal we can actually have from this charge 4e superconductivity is that here you would have half flux without ever having any kind of defined spin current circulation at all, and that would actually show up as a shot noise signal.
Yeah, so going back to earlier in your talk, I know one of the reasons you were looking at this experiment was to try to discriminate between triplet and singlet superconductivity. So, this sounds very compelling, but we do know that there is substantial spin-orbit coupling in strontium ruthenate. If the strontium ruthenate is a singlet superconductor, is there any way to account for this long proximity effect, or is that still a strong piece of evidence of triplet pairing?
Actually, thank you very much for your question. Really, the question you're asking is that, are we sure that this actually means that you have spin triplet pairing way into the bulk, or is this just interfacial phenomena? Right. And I think, this kind of the experiment they're trying to do may actually answer this question, because now they can make superconducting strontium 214 thin film. Right. And the fact is that the spin dissipation that would occur in this kind of setup, this would be very different if you just have an interfacial spin triplet versus you have bulk spin triplet superconductivity. Because after all, Cooper pair spin current can occur way deep into the bulk if you have this bulk spin triplet order parameter. So that would give you a completely different spin dissipation channel depending on whether you have bulk spin triplet superconductor or this just an interfacial spin triplet superconductor.
And those experiments are in
Well, yeah, they have planned for fabricating both this kind of heterostructure and 214 samples of different thickness.
Did that answer the question?
Yeah.
Related to Steve's question, so if ruthenates a triplet superconductor, presumably spin waves are not gapless because of spin orbit coupling. There should be a gap. So how do you have any idea how big this gap is?
That was actually, thank you very much for that. I owe you big thanks for that question, because basically here the reason why I had this Zeeman field applied is to make sure that you're going to have xy plane is going to be the easy plane. So in here, I was just showing xy plane being the easy plane. So there was no, so the external magnetic Zeeman field kind of raised out the effect you just mentioned. On the other hand, for this AC setup, you see, I wasn't having any kind of applied Zeeman field, and the conventional view had been that actually the c-axis is like the natural direction for the d vector, and in that case, the energy scale you're talking about is like the analog of the mass of the pendulum. So, I mean, people are having very huge difficulty trying to estimate the magnitude here. The guess has been that whereas the similar energy scale in helium-3 arises from the dipole-dipole interaction between helium-3 atoms, here they must be principally arising from the atomic spin-orbit coupling of the ruthenium atom.